basically this concept was proposed a long time back, um, and the proposal there is a paper by Von Cannell in 1990 October, Journal of Solid State Circuits, which basically talks about this scheme where you have a digital circuit whose voltage is adjusted to be low enough uh, and to be just enough so that the speed of the digital circuit meets the target speed. And the way the author proposed to do that was basically have a digital circuit whose voltage comes from a voltage regulator. So this is a simple voltage regulator circuit where you have an external supply, but the supply which is actually given to the circuit comes, there's a drop out here across this device, and it is this op amp kind of sets this voltage such that you based on certain consideration such that this voltage is a regulated voltage. Typically in a voltage regulator, what happens is that there is a specific target voltage which is given as a reference of some kind to this op amp, and the op amp basically tries to generate an output voltage such that the generated voltage matches the target voltage. Here the target voltage is not a voltage, there's no specification as to what the voltage is. It's coming from the time domain. That is, the voltage should be such that the delay of the critical path under this voltage matches the delay of the actual critical path. Right? So this is the high level concept. That means you want to have a target delay. That is what basically is the feedback given to this voltage generator. Now the thing is, how do you know what is the actual delay of a critical path? As we had discussed, there can be many different critical paths, and some of these paths can be quite complicated. You will have lots of logic gates, some wiring. It could also go through memory structures and so on. So, and you can have millions of paths. Modern chips, you have multi-million gates. You can have lots of paths and many thousands of critical paths. So, of course, the ideal would be to actually measure the delay of actual critical paths, and we'll see how that could be done in one of the subsequent lectures. What is an alternative approach is to, if you have a mimic of the actual critical path, right, what is called replica, then you can measure the delay on the replica and do whatever you want to do using the replica. Now, the key assumption is that whatever replica you have, it tracks the delay of the actual critical paths. Track over what? Over process variations, over temperature fluctuations, over aging, for example. So the simplest way to do that is to have a chain of inverters. And what you do is you analyze your design. You do your design, you do your place and route and so on. So you have actual layout, so you have actual wiring parasitics. Then you analyze the delay of your critical paths from your circuit. Then you create the inverter chain, you tune it, put the right number of stages in the inverter chain such that the delay of the inverter chain is at least that much of the critical path. Perhaps you give a little bit extra margin to cover for variations. Now that inverter chain, actually if you study the variation of the delay of the inverter chain over different process conditions, you will find that it tracks reasonably well. I mean, there will be some deviation, but largely it will track well with the delay of the actual critical paths. So basically you can now use the delay of the inverter chain as a proxy for the delay of the actual critical path. So now the inverter chain, if you fold it, if you have odd number of stages and you fold it into a ring, it becomes a ring oscillator. So then you can just measure the frequency of the ring oscillator. Either you could measure the delay directly of the delay chain, or you can measure the frequency. We'll see how you can measure the delay of the inverter chain. But measuring the frequency is again pretty straightforward. So here what you do is, for example, here we know that this has to be part of a feedback loop, right? So you want to achieve a certain target frequency. So let us say that we have a certain target frequency, Fin, and then you have a VCO made out of delay chains, which has a frequency which is n times Fin. Okay, n is under your control. You kind of pick a suitable number n, and then you have a divider VCO frequency is divided down, and then the feedback loop tries to adjust the voltage, regulated voltage, such that the frequency of the VCO matches the frequency, the input reference frequency, right? And so the error is taken, it's basically amplified, filtered. This is a standard control system, right? You have to do whatever is required to make a stable control system, and you generate the regulated voltage. So this control loop is adjusting the supply voltage such that this VCO meets the target frequency, and with the assumption that the VCO has been designed to track the actual circuit critical paths, the same voltage when it's applied to the digital system, the critical paths will also adhere to that delay. They will not violate the delay, and so the whole system will work properly. That is basically the approach here.
Sir,
yeah.
in these circuits, all these phase data and the VCO, are we changing the supply voltage of that also, or we are keeping the supply voltage constant and we are just changing supply voltage in the system?
Okay, so the question which is being asked is, would you also change the supply voltage of these three components here? The phase frequency detector, of course here they've shown it as phase detector, you actually have a phase frequency detector, a charge pump and a loop filter. Would you change the supply voltage of those? Now what happens is that there have been some approaches where even those can be adjusted, but one thing you have to watch out for here is that firstly these are analog circuits, right? Charge pump is essentially a current source which is dumping or removing current from a capacitor, right? That is essentially charge. You're putting some charge, taking out some charge. So the current source is an analog circuit. They have said there is a loop filter here, but there has to be also a voltage regulator which is not shown here, which is similar to what we saw the op-amp controlling PMOS. So that op-amp is also analog. The question is, as you move around the, because as this loop is working, it's trying to adjust the supply voltage. So the same supply voltage which you are adjusting is also being, if you go and adjust the voltage of the charge pump as well as the op-amp, it might actually not work properly. Okay, so there could be a lot of problems in trying to get that to work. And so, you kind of don't want to get into that kind of a complication, mainly because these circuits are supposed to be very low power consumption circuits. Okay, you should not be consuming too much power. So there's no point in complicating your life and trying to reduce the power of these anymore. So, and these are very critical, because if this doesn't work, none of the system works. So this has to be very conservatively done, right? Because if you mess up generating the right voltage, if it oscillates and the voltage is not stable, then you will have a problem. So you don't want to do that. So since 1990, a lot of papers have come where people, initially it was just an academic curiosity, but now even commercial chips have started adopting some of these techniques. Usually I find there's at least a 10-year difference, a 10-year gap between something being proposed as a research concept which comes up in one of these papers, one of these IEEE papers, and then it getting adopted in a commercial product. It can take up to 10 years or more. So, because industry is always conservative in a lot of these things, it takes time. They need to be really convinced, and they need to be really put under, there has to be no, they won't adopt a risky approach unless there is really pressure to do it for some reason, right? Because you want to be safe, not take risks. As if you can avoid risk, that is better. So, but now you see in 2005, there's this paper from Japanese group, which is actually probably from Sony, where they talk of DBFM system for their large chip, system on chip. And DBFM is dynamic voltage and frequency management. So there are two components. One is you identify the frequency of operation for the chip, which can be time varying. You break up the operation into time phases. Each phase you figure out what should be the right frequency of operation for that phase. You set the frequency for that, and for that frequency of operation, you find out what is the lowest voltage which will meet that frequency, so that you minimize the power. So you are optimizing power by adjusting the frequency, so that helps the dynamic power CV square F. In addition, you also reduce the voltage, so dynamic power as well as leakage power both get reduced. So you have dynamic frequency control, dynamic voltage control. How is frequency adjusted? In a particular phase of operation, you just monitor the activity of various components in the chip. Embedded DRAM controller, right? There will be a controller to control the embedded DRAM, where you would make a request to fetch from the DRAM. So the DRAM controller will have an idea for, okay, now a fetch has come in this cycle. So you just keep track how many times a fetch or access request has come. Similarly, bus control. There will be a bus on which all the components in the SoC are connected to. Anyone who wants to access the bus has to make a request, right? That request will go to a bus controller, which is essentially an arbiter, because multiple people want to use the bus. So the arbiter of the bus controller will decide whom to give access of the bus. So again, there you have visibility on the activity of the bus. Then you have a processor. Here they are using an ARM processor. So again, is the processor in an idle state or a non-idle state? So like that, you can kind of keep track of, there will be one enable signal from each of these, which you feed it into a counter. So activity monitor is nothing but a counter. So over that phase of observation, you count how many times, how many cycles were these things active. And based on that, you adjust the frequency of operation for the next phase. Once the way you adjust the frequency is set up the clock generator to generate now the target frequency. And then you have the voltage DVC, dynamic voltage controller, which now goes ahead and identifies the right voltage to operate for that frequency, right? The lowest voltage where the circuit will operate correctly. So one of the key components there is this same delay monitor, which they are calling it as delay synthesizer. Okay, so the delay synthesizer's job is to synthesize a delay, which mimics the delay of the critical path. Okay, so the target, so you excite the delay synthesizer by a pulse, by an edge. As the edge travels down, so you launch an edge for a rising edge, right? So that edge is launched into the delay synthesizer, and after some delay, the edge comes out, and then you have some number of buffer stages, right? And the edge might propagate some distance in this, think of it as a racetrack, it's kind of propagating some distance. So by the next clock edge, you activate all these flops. One flop is sampling the signal at the input to this delay line gauge, next is the next stage, etc., etc. So what you have done is, when the following clock edge comes, you are essentially taking a snapshot of how far the input edge is propagated in this, right? So for example, I mean here the edge has propagated up to this point, the third point, right? This is one, this is one, this is one, this is not yet turned 1, it's in the process of turning to 1, it's still 0. So when the next, the capture edge comes, yeah, it's capturing a 1, 1, 1, and then everything else is 0. So then you encode this, right? What do you encode? You encode where is the transition from 1 to 0. So here the encoder will give an answer 3, right, or 0, 2, depending on whether you start counting from 0 or start counting from 1. Essentially, you are getting a number which is essentially capturing where this transition is happening. That number you take. Now, what you have to do is you have to essentially adjust the supply voltage of this delay synthesizer of this thing, such that the edge has traveled a certain distance, right? And if the edge, for example, for a particular voltage travels too far out here, right? Say you say my target is I want it to travel exactly 3 units, this plus another 3 units out here. Say that is your target. Why is that good? Why do you want to keep that as a target? Basically, what you're saying is, for that particular voltage, the delay of my critical path is, I'm allowing for delay of critical path to be the delay of this synthesizer plus a sum of these 3 buffers. If you match the delay synthesizer to exactly match the critical path, this extra 3 buffers is giving you some extra margin, because you can never be sure that you are perfectly matched. So how much margin you want to give can be controlled by adjusting this target. In your feedback loop, you can decide to set the target to be 2, 3, 4, 5, depending on how aggressive you feel your delay synthesizer, how well it's matching that. Now, if the voltage is very high, what will happen? That means the delays are very fast. So when you launch an edge here, by the time the next edge comes, the signal would have traveled very long distance out here, because the delays are all small. So then the encoder will give you a code which is much higher than your target. If your code is higher than your target, you know that your voltage is high, you reduce the voltage. Similarly, when the code is less than your target, you know that the delays are slower, so you increase it. So that's how the feedback loop will work to adjust the supply voltage here. Okay, so the delay synthesizer will essentially consists of a number of different components, 2 input gates, some metal pieces of metal track, or you have a long metal track and you can tap off from different sections to mimic different amounts of wiring delay, some fan out, loaded inverters. And the idea here is that you make this delay synthesizer once and then use it for all different kinds of products. Only thing is you can then program this mux selection to decide how many of each kind you want to put in your delay synthesizer, so that mimics the critical paths of that particular product. Okay. So what they find is that this delay synthesizer actually, which has this combination of NAND2, etc., seems to match better with the actual critical path. So what is shown out here on this graph is with supply voltage, how does the delay synthesizer's delay track that of the actual circuitry for 3 different process conditions: slow, typical, fast. Slow means threshold voltages of all the transistors is higher than normal. Fast means threshold voltages are less than normal or typical, right? Less than the typical. So they have some amount of margin out here, right? And that margin is reduced if instead of using just NAND2 gates, they have this mix of gates and wiring and so on. And they are able to mimic the delays much better. So when they do that, what they find is that when they are operating, at a certain frequency, target frequency, because this is a SoC which is some kind of a media processor chip. In media processors, typically there is a target frequency which is set, right? Because you are operating, say, on video frames coming in, there is a certain rate at which video frames are coming in, so you have to operate at a certain target frequency. Now, if in the conventional approach, you would ensure that even the slowest process corner, you are operating at that frequency. So, which means that you select a supply voltage, and which will be larger than normal supply voltage because it's a slow process. Thresholds are higher, so transistors are weaker. So you need to increase the supply voltage to get the speed. When they do that, you find that you're burning 572 milliwatts. Now, if you didn't do anything and you kept it at that same voltage under normal and fast process conditions, you are basically, what you're doing is you're operating at voltages much higher than what is required. And so you burn extra power unnecessarily. So in fact, you find that the power actually goes up when you're operating at the same frequency, but the process is faster, leakier process. So some chips will burn 645 milliwatts and most other chips will be out here, right? Burning about, some 600 milliwatts or so. But as soon as you turn on the dynamic voltage control, because the delay synthesizer is in some sense sampling the process, right? The delay, if the process is fast, for the same voltage, the delay synthesizer will tell you that, okay, the process is fast because delays are happening, delays are shorter. So the feedback loop will go and adjust such that you again get back the delay you want. So with that, what happens is that the you can save power with this dynamic voltage control. And under fast process conditions, the supply voltage is reduced so that actually the total power actually comes down. So we saw the activity monitor is basically just counter to count up the number of cycles when these entities were active. And there is just an OR gate because we don't care which one, so at least one is active. And this counter is reset with a fixed timer. You reset it, then you count up till the next time the timer fires. So in that time you collect and see how many times the bus was active, and based on that you adjust the frequency. Yeah. Pardon? I'm sorry, yeah. So you couldn't hear what I said? Is that what you're saying? Right. Basically, what I was just saying that the way you measure the activity is you set the timer, maybe you count the number of active cycles in a million clock cycle period, right? You set up the timer. Timer is just a counter which is running off a fixed frequency clock, right? So you say after so many million cycles, in that duration, let me count the number of times at least one of these were active, right? So that gives you an idea for how often or how busy the chip is. If that number, and use that number then to decide whether you want to increase the frequency or reduce the frequency, right? So, for example, you might have, you might give a margin of 10%, right? I mean, say for example, you're counting 10 million cycles, say 1 million cycles, then you might give a margin of 0.1 million cycles and say my frequency should be about 0.9. Right? That is my ideal target. Right? Suppose you say that is the ideal target. Then based on the actual activity measurement, you decide whether you are close there or not. If your actual operating frequency is much higher than your target plus margin, then you either adjust up or down based on wherever you are. Right? So this is a very simple common sense, algorithm to adjust the frequency.
The timer will work on directly PLL frequency or
The timer will work on a fixed frequency clock. Okay, this is not the frequency adjusted frequency clock. It is a fixed frequency clock.
so it's getting directly from this PLL source or
It could be PLL source. It could be some other reference coming from outside. Yeah. So if the PLL is locked to an external frequency and the PLL itself you are not changing the frequency, then you can draw from there. Because how do you adjust the frequency? There are two ways. You can just change the division factor. You have a fixed frequency source and you just change the division factor. But that only allows you to get coarse steps, f by 2, f by 3, f by 4, etc. But if you want frequencies in between, then you have to adjust the PLL, right? So then the PLL frequency itself changes. So, but no matter what, there will always be a fixed reference coming in with an external crystal and so on. So you can use that to derive your fixed frequency clock. So in this, so since that time, okay, so further work, this is a recent paper in 2012 by again another Japanese group, where they look at this problem of generating this delay synthesizer, right? What is this delay synthesizer? Very early on we saw it was just a simple bunch of inverters by that early paper we saw, then this bunch of gates and wiring and so on. So now these guys are basically looking at that problem again, and they look at, some other people, what they do is they actually take the actual critical paths. You might have number of critical paths, and your critical paths could consist of a sequence of gates. We don't know what logic gates, it really depends on your circuit. You pick the worst of them, then you replicate that again. You replicate the critical path by actually instantiating only the gates of that path separately. And you say, look, that is going to be my delay monitor. Now, you have to be a little careful in the sense that the layout you'll not be able to replicate exactly, because in the actual critical path, the chain of gates through which the signal flows might be all over the place, because you have no control when you are doing synthesis, place and route. So the exact layout you will not be able to replicate, but at least you will be able to, maybe you can put in the replica path, you have the same sequence of gates, and then you have to somehow put in extra wiring load to capture the actual wiring load like that. So that could be your replica critical path. And that is an approach which number of people do take. Now, what these guys do is they kind of say that, look, that is, instead of doing that, let us go back to a delay line which is consisting of known gates, standard gates, and they show that it actually works quite well. And the reason, and they find that it actually, and you can also tune it. The same design, just like in the previous Nakai paper, by adjusting the mux settings. Something similar they are able to do by adjusting in a digital way, not the way Nakai did by adjusting the mux setting. They have a different way of adjusting the values so that it can match the critical paths of different products. Okay. Now, if you were to take the replica of the actual critical paths, you anyway have a problem because again it's a little, okay, you have the same sequence of gauge, but the layout you cannot reproduce. You still have to do some fudging to kind of match it, right? So, and then every new product you have to redo it again and again. So instead of doing that, why not just go back to a simple known delay line? And anyway, I have to tune it for each different product. I'll just tune it in a different way instead of trying to extract the critical path and replicating it. Now, the two issues are when you tune it, you have to give a margin, right? The delay monitor which you have put, there has to be some margin with respect to the actual critical path. That margin, how does that margin vary? I mean, what is the variation of that with respect to the actual critical paths across process, temperature, and aging? And secondly, where should this monitor be placed in the chip? If especially some of the SOCs are very large, there can be substantial variations across the die, right? When you go from one portion of the die to another portion of the die, there can be large variation. Even the temperature can vary a lot. Some portion might be very hot, another portion might have mainly memories and not much active and might be cold, might be cooler, and the process itself could vary and so on. So that is another problem you have to worry about. Where should this be put? Okay. Now, before I get into that, this aging, what exactly is this aging, right? So aging is, like for us humans, as we grow older, our faculties start dimming, right? We are no longer as smart and fit as we should be. So the same thing happens with the chip. Now, right? So what exactly happens in humans, right? Why do we age? Okay, that is a question for the biologists. Right? So what is aging? Why do we, biologically, or if you look inside the cell, what is happening? That is where a lot of active research is going on. And I don't know whether you saw a news report recently about how some of these scientists are able to prevent aging by doing something to the skin cells, and the skin doesn't age as much as it would by this small modification. Just turns out there is some counter in there. Each cell has these counters, and every time a cell divides, the counter decrements. If the counter decrements below a certain value, the cell dies. Apoptosis, as they say. But by keeping the counter alive, by adding extra stages to the counter, they are able to keep the cell alive for a longer period. Sometimes the problem is when the counter doesn't work properly and gets stuck, you have also cancer, right? Tumor. So it's a very dangerous, slippery slope to be on. In the case of a transistor, what happens, right? So something, again, equivalently you have to see what are the physical mechanisms which are changing the characteristic of the transistor. So one of them is that, essentially it has got to do with the oxide, right? You can start degrading the oxide, perhaps due to various reasons. With heavy electric fields, you start creating punctures in the oxide, and then it's no longer as insulating as it should be. Another thing which is related to, which has this name, which has this acronym BTI, bias temperature instability, right? So it is either NBTI, negative bias temperature instability for PMOSes, or PBTI, positive bias temperature instability for NMOSes. For example, in the case of a PMOS, again, a very important region for any transistor is the interface between the oxide and the channel. You have a single crystalline silicon, but at the surface, the bonds are dangling, right? So that is where you always have issues related to mobility, performance issues, etc. So those bonds have to be passivated, and you might have some ions like hydrogen ions and so on. And then if you have a prolonged, for example, in the case of a PMOS, if the PFET gate, when you turn on the PMOS transistor, the gate is at ground compared to it's at the negative voltage compared to the source, right? That is why it's called negative bias. When you do that, you're pulling positive ions from the surface of the oxide towards the gate. And that migration can happen slowly, or it's not instantaneous. Over time, over days or weeks or months or years or whatever is the time scale, slowly the ions will keep moving. They'll shift. Now the threshold voltage of the transistor depends on the location of the ions. If the ions come closer and closer to the gate, the positive ions, what does it mean? It means that some of the charges, negative charge in the gate is getting compensated by these ions, right? So if I want to invert the channel, I need to put more voltage and more to invert the channel, which means the threshold voltage essentially increases. The closer the ions come, the higher is the threshold voltage. So what is happening? The transistors are becoming slower because the threshold voltage increases, right? So this is a problem. So what that means is that I have a critical path at, as soon as a manufactured chip, the path has a certain delay, but over time the delay of the path can slow down. Especially if path consists of gates whose always, you have the voltages are, you're keeping the transistors always on, for example, right? So then those become slower and slower. So certain circuit techniques have also been developed to try to avoid that, try to not keep things on, for prolonged periods of time. But regardless of that, the point is things become slower. So after 5 years from when you manufacture the product, or 10 years, whatever is the expected lifetime, if it's a cell phone, perhaps 2 years, right? The way which people are changing cell phones. But you have to ensure that you give a margin for aging also. Yeah, question.
You can invert the voltage and those carries which are trapped near the outside, they will go back.
Correct. So the suggestion is, can you not, instead of keeping a negative voltage for the gate, give a positive voltage and push the carrier back? And that is exactly what is done, is to ensure that you don't keep a constant DC bias. Try to avoid that. Right? You try to keep voltages which are toggling between negative to positive. Okay, so that was a small aside on aging, but coming back to the delay line, what Ikenaga proposes is a delay line consisting not of inverters, but these inverters which have 2 transistors in series stack for both PMOS and NMOS. And these guys are configured in a ring. Now, you measure the delay of the ring. And one way to measure the delay of the ring is to actually, a simple way, without getting into analog circuits and so on, is to actually do a measurement over some period of time and observe. If you have a fixed time window, you just see number of times the output of the ring, number of edges coming out here, right? Essentially, you're measuring the frequency, essentially, or the period of the ring. You give a certain time window and just count how many periods fit into that time window, and that you can count easily using a counter. So you have an all digital way of measuring the period, because this is something which again, it depends on what bandwidth you want, how fast you want to make this measurement. When you do the measurement in this approach, you're saying, look, I'm going to count for over a period of 1,000 cycles. So just like what we saw with the previous, where you have a timer which gives you a certain time window in which you have to make a measurement. Similarly, there will be a timer which will say, okay, I'm going to start the counter. Let me see by the end of the timer how many counts have happened. That gives you an indication, and you know the time period because that is a fixed frequency clock. So from that you can estimate the frequency out here. So this is a digital approach, but you have to spend more time to make the frequency measurement. Now this delay, these rings, they place it at multiple points in the chip so that you average the readings from all the different points. Because what you want to do is, you have a certain chip, and the chip, there is a certain variation of the process across the chip, what is called within die variability. So the critical path, say maybe on this corner of the chip, say the same critical path, if you were to put it here, the delay will be a little different. The same critical path on this side will be a little different, and so on. Okay, that is because of within the chip itself there are some variations. So then, what should my delay monitor estimate, right? The delay monitor, there are 2 ways. Either I estimate the worst delay or I estimate the average delay. Okay, no matter what I estimate, whatever delay I estimate, I need to put a little padding on that and say that is going to be my critical path estimate. So what they show in this paper is that average is a better way of estimating. So they put multiple of these guys and then they average out the readings from all these counters, which is just a simple adder. And to that, what they do is they put a little factor alpha, because remember, for every chip, the actual critical paths will be not exactly the same as what the monitor gives, but some factor, right? That factor alpha you have to find out and put. That is basically so that you are tuning, that is the tuning portion. You tune your delay lines to that particular product by figuring out what the alpha is, and that product gives me the actual critical path estimate of the actual critical path delay, which then you put it into your feedback loop to adjust and get to where you want, right? So that goes to your power control. So the delay line is configured as a ring with counters used to measure the delay. So it's an all digital approach to measure delay. Right? Whereas if you remember the PLL approach, it is you basically have a phase lock loop with a charge pump, so it's kind of a semi-analog approach. The other approach with the delay line is also digital approach. Now the multiplication factor alpha is what is used to tune the delay line to a particular product. By choosing the right value of alpha, you can give the margin and then cover for and then ensure that whatever number T monitor times alpha is the estimate of the critical path.
Sir, why are you using 2 and not stacking?
So the question is, why have they used 2 stack of 2? We'll see that next. Now the thing is that what they do is that they basically what they do is they study the number of gates in their particular SOC. They have taken a number of SOCs they have designed, and they look at all the gates which are being used, right? And they classify the gate based on the P stack and the N stack. So 4:1 means that particular those classes of gates have 4 series PMOSs, 1 NMOS, etc., etc. And they find that the dominant gates they have used in their SOCs are 2:2. That means they have a 2 PMOS stack and 2 NMOS stack. It doesn't mean that this is the exact gate they are using. It's just that if you analyze the pull-up and pull-down structure of the standard cells, they find a series path of 2 for PMOS and series path. The inputs might be coming from different places and so on. So that's why they say that they will use, and this is only the 100 critical paths of a 40 nanometer SoC. So in those critical paths they analyze and they find this is the most dominant. And so they use that, and then they what they do is they compare the delay of their universal delay line with the delay of the critical paths, and what they find is that across different process corners, so this is just a schematic to show, right? So say you have 2 different critical paths, schematically, conceptually, what should alpha be, right? So let us say if you look at the ratio of the critical path to the monitor, delay of the monitor. So this is the monitor, that is a certain delay, right? And then the critical path has a certain delay. This is one critical path, this is another critical path. The paths are different, they have different gate structures, different amount of wiring and so on. You take the ratio of those 2. Now, if the ratio is exactly the same, some ratio, it doesn't have to be 1, it's some factor alpha, then you can program that alpha in there and you are done, because then you say my monitor gives me some number, I'm going to put in this factor alpha, and that alpha I somehow figure out, and then alpha times that value of the monitor is the delay of the critical path, right? But what you find is that there is no single alpha which will give you the exact ratio. It depends on the process conditions, right? Depending on the process condition, this ratio can change, and that is what they mean when they say that there is an alpha, and then there is a small factor delta alpha I need to put in. 1 plus delta alpha times alpha is the actual factor, because then that will ensure that if I put in that number, it will cover the topmost portion, right? The topmost portion. So that delta alpha I have to extract by comparing the delay of whatever delay monitor I use with all the critical paths. Then you choose the worst one and say that is the factor delta alpha I need to put in, right? So that is what basically what they find is that, so here what they are doing, they are looking at delay lines made out of these 2 stacks. See, initially they had some idea that okay, this 2 stack is 2:2 is the best, but to confirm that, they actually make a delay line with the 2:2, and then they look at this factor delta alpha, right? That means they look at 100 critical paths, they look at the ratio of the 100 critical paths to the delay of the delay line across these process conditions. across these process conditions, and they find that the 2:2:1 mimics gives me the best match. That means the deviation is the least with 2:2. Whereas if you were to use 1:3, 1:4, any of these others, the deviation is much larger. That means I need to put in an extra margin. Here the extra margin is 0.109 or something, whereas here it is 0.167 and so on. So you have to give extra margin if you were to use any other delay line.
This kind of analogous with the use of replica as a delay synthesizer, right?
Instead of using replica,
Yeah.
what you are using is you are using the universal delay line, but you are comparing with the 100 critical paths in your SOC, and you are seeing how well does it track, right? It doesn't track perfectly. If it were to track perfectly, delta alpha would be 0. There is some variation, but that variation is the smallest. There is some variation, right? If it were to track perfectly, the ratio of your delay line with the critical path delay would be same for all the critical paths, but you cannot expect it to happen. There will be some deviation, but the deviation is the least if they use this, because most of the critical paths seem to have 2:2 type stacking structure, so it matches the best is what they are saying.
So this universal delay line is configurable or not? They are fixed.
This will be fixed because the way they achieve tuning to different products, where you might have different lengths of your critical paths, right? Another product might have a different length, is by adjusting the multiplication factor alpha.
So the previous game we were changing supply voltage to configure to match the delay of delay line and the
No. Okay. So the question is, see, there are two. So the supply voltage adjustment is done because that is part of DBS or ABS. We are not, that is independent of this. No matter which delay monitor you create, right? You still have to adjust the supply voltage such that the delay monitor's delay meets your target delay. And that voltage will be the lowest voltage. That you have to do. Now, we are asking the question, what should be the structure of the delay monitor? Which one matches the critical path the best? No matter what you use, you still have to adjust the supply voltage. Now, the previous paper by Nakai had a delay monitor which itself was configurable. Right? You had some muxes and so on. You could change the proportion of NAND to inverter and wiring and so on. Right? That configuration is different. You do it one time. Right? For a particular product, you figure out what the configuration setting is and you do it, and that's it. That is not part of the feedback loop at all. Feedback loop per chip is just adjusting the supply voltage. Here, the configuration is done not by adjusting the number of stages of the delay line, but by because there is a completely digital approach. Right? They create that, they multiply it with a factor alpha. That alpha you can configure and adjust. So that's basically what they do here. Now they also look at, they say that, look, let me also compare the performance of this by, instead of using this delay monitor made out of these 2:2 inverters, let me take one of the critical paths and make that as the delay monitor. I make a copy of that critical path, just like we discussed earlier. You instantiate the same gates in the same sequence. For the layout, you have to kind of do some fudging with the wiring and so on. Now you say, look, that is going to be a critical path. But what they find is that critical path also doesn't do as well. It will do very well to match its own. That is where you get this one. Right? This one for this particular, so here what they have plotted is the delay of their critical path. They have chosen one critical path, which happens to be this, and there are 100 of them. So there are 100 points on the x-axis, and then that particular one matches well with itself. But with the others, it doesn't match very well. Whereas the universal delay line, it seems to match well, with not too much of a loss. So that is why, again, this is another study they do, and to kind of convince themselves that this is the
Rescue.
okay, yeah. So we're almost done. So basically now, remember we said that you have 4 you have this variation within the die, and you have these monitors all over the place. So you could choose either an average or a max. Now when you take an average, what happens? If the individual monitor has a spread like this, when you average, the spread comes down, right? Averaging helps to bring down the spread. Whereas if you take the max, you have a slightly different statistic, and I'll kind of not go into, maybe you can, some of you who are interested in these kind of probabilistic analysis, you can see what they are claiming works out. That is, average is better than max as a candidate, right? But that is basically what they are claiming. So with that, I'll stop here.